Today we will look at stock span problem. So by span, what is the meaning of span? So these are, let's say, these denote the prices of stocks on different dates. This is on some date, this is on next date, next date. So when we are looking at any day, the span denotes that preceding dates for how many days consecutive the price was less than or equal to current price. So today it's equal to current price, so include that. Here it's less, so we increment the count to 2, and we go here, it's more than today's price. This is today. We don't know the future prices, so we will not look at the right side, only today and left side. So here the span will be 2. So we will solve this problem with starting with simple approach, then we will gradually improve our time and space complexity for this. So let's look at an example. So these are the prices on different dates, and in first call in LeetCode they want us to implement next function, and here they will give one price. This will be today's price. So first time you get 100, next 100. So you have to come up with some data structure and how you will store these prices and how you will store the spans. So for each day there will be one span. In particular for first day it has to be 1 because there is nothing to the left of it. So only today's price is included and it's equal to today's price. So less than or equal to starting from today till and going towards left. And there should be no break. As soon as you get a higher price, you stop. That is the span of today's price. So how you will store it? So let's store everything in array to start with. I will store all the prices and I will store all the spans. So for next 100, I see that size is 0. So I will store 1 here. Then there will be a call of next 80. So we get come here, we look at today's price, we start with 1 and we go left. We see that the leftmost is higher. So we stop. So it will be 1 again. Next 60 comes, and here we know that there are 3, 6, 7 calls. But let's assume that you don't know this. You just know whatever has been called, but you don't know the future. So next, when 60 is called, you see that what is the left? Left is greater, so you stop 1. Next 70. So you look at left, it's smaller. So you again look left. So increment the count and go left. And stop when you reach a higher price. So you look left, smaller. Again left, larger. So you stop. So it's 2 here. Now 60, you look left, it's larger. So 1. Here it's smaller, 60. So plus 1. Then go to 70. 70 is also less than 75. So next one 60. 60 is also smaller. Next one 80. 80 is larger. So you stop and the value is 4. Next 85. Smaller, 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 larger. So here value will be 6. So this is the very basic approach. And we take one step at a time. We look at all the previous prices until we reach a higher price. And we store the prices and span everything. So this is a valid way, but this is very unoptimized. So how can we optimize it? So let's say the left price is higher. So this is current price. So you look at left price. If it's higher, then you don't need to do anything. Its span will be 1. So in this case, a span will be 1. But let's say we have a price and the left price is smaller. Then you know that at least span has become 2, current and this. But instead of looking immediate left, let's say this span of this day was 5. What does the 5 denote? That there are 4 more smaller bars than smaller prices than this price. So this is denoted by the span of this. So if this price n-1 or k-1th price, this is k, is smaller than current price, and there are 4 more prices which are smaller than even k minus 1, then these will also be smaller than current price since it's larger than this immediate left. So at least span is now 6, that is one more than this. So straight away we can come here. So we will skip these 4 elements. These are guaranteed to be smaller, that's why its span is 5. So immediately we jump to 5th element here. So if immediate left is larger, nothing to do, order 1. But if immediate is less than current, then we look at span. This tells that don't need to check these many prices. I have already checked. That's why my span is 5. So you can directly jump to 5th. And you can come here and check this price with the current price. If it's larger, then you stop here, return this index minus this index. This is the span. But if it's smaller, again you will see its span. Let's say it's smaller and its span is 3. So you know that there are 2 smaller prices than this one. And this is smaller than this. So no need to check this, straight away jump here and do the check. So this way you will be removing many redundant checks. So this will be optimized in terms of time. So how can we modify our solution here? So let's say we are here at 75. We are trying to calculate this and we have calculated everything to the left. So we look at immediate left. It's smaller and its span is 1. So 1 does not help, but let's follow this trend. So we come here. We again compare this 70 with 75. Again smaller. We see its span. Its span is 2. So we jump 2 steps. No need to compare 60. We come here and again compare. Now it's larger. So you subtract this index. So this is 0, 1, 2. This is 1, 2, 3, 4, 5. So 5 minus 1 is 4. So its span is 4. Next you come here. You see immediate left. It's smaller. It's smaller by 4. So you straight away jump 4 steps. 1, 1, 2, 3, 4. So you straight away jump here. So you see you have skipped all these comparisons. So straight away jump here. And we see that it's again smaller. So we again jump here. And then we get the larger. So now it's 6 minus 0 is 6. So its span will be 6. So this will be the optimization. So I will write the code for this. This will be time optimized. But later I will suggest you how we can optimize the space also. Here we are storing everything. But we can do similar optimization for space as well. And why is that? Let's say we are looking at this price. So while calculating next, it's useful. But once we have calculated this, will this be ever used? No. Why? Because this is guarded by this one. So if it's larger than, if the immediate next is larger than this one, whatever comparison comes from left, it will hit this one and it will look at its span. So since it's smaller, it will never compare this one and it will straight away go to values larger than this. So it can directly come here if it's coming from right side. So all of these are redundant. So the same jump, what we are doing, this jump denotes that intermediate values are not useful. So we can use a stack in place of vector. So first let's write the vector solution where we store every price and that will be time optimized. I will not write that trivial case where we compare every price. We will directly implement this jumped checking, that is optimized time. So let's start. So I will write it in C++ first. So what do we need in this class? We have to implement this class itself. So we will have 2 variables. You can also have one vector and each element can be a pair, span and price, but let's keep it separate. and nothing to initialize in constructor. And next, so let's start with index. Index will be the current index, and that will be size -1. So when nothing is inserted yet, the index will be -1. While idx greater than equal to 0 and prices idx is less than equal to price. Price is the today's price. So till we get a higher price, we continue decrementing the index. Using that span, we will continue jumping that index to the left. Int span equal to spans idx. So it will not check for 0th or first price here, since index will be -1. idx equal to idx minus span. So exact same thing what we saw in the explanation. And then we push the current price. So when this loop ends, we would have reached at an index whose price is higher than current price. So we will, after inserting whatever is the index of this, which is prices.size -1. So first element is inserted, it will be 0 minus idx. So what we did there in the PPT. So here, whatever is the current index and whatever is the higher price, you just subtract those indices and you get the current span, and that will be stored in this spans. So spans dot pushback span, and we also return a span. So let's try it. If we don't take this step, you can think of it as 1 every time instead of checking the span. Then it will look for all the elements. So this is the optimization here. So this works as expected. 2146. So let's submit. And the solution is accepted in C++. Now it's optimized for time, but how can we optimize it further for space? So I'm giving just a rough idea. You can try it. It would be a good exercise. And it's not necessarily guaranteed to optimize, but in general case, on average case scenario, it should optimize. So you can have one stack, and what you can write, this stack is S. You can have a stack of pairs, or you can have separate stacks like this for spans and price. So you can check while not s.empty, or instead of s, let's call it prices. And prices.top is less than equal to price. Exact same thing, the same logic that we used for skipping comparisons, we will use for this stack. So all those elements that we skip will never be used. So we can pop that from the stack. So here we will do that thing. So we can have some count here, initialized to 1, since minimum it will be 1, the span. And then we keep incrementing the count. Count plus equal to prices dot top or spans dot top, and then also prices dot pop. So we will pop all those intermediate values and keep adding to the count, and finally we will push the new price. New price will always be at the top of stack. So we will push the price and also the new span or the result count. If you are keeping it separately, two stacks, then push them separately. Otherwise, you are keeping a pair, you push them as a pair. So this is the space optimization that you can try. So I'm skipping that. We will use this optimized solution for Java and Python as well. So constructor is done. Next, we will do this next. And this solution works in Java as well. So let's submit. And it's accepted in Java. Finally, we will write it in in Python 3. So let me again copy it. So constructor is done. Now let's copy it. So it works. So let's submit. And the solution is accepted in Python as well. So please don't forget to implement that space optimization where we don't need to store the values which we are skipping. So keep a stack. Its top will always hold the current price and the current span that we calculate here. So whatever we are appending here, we will push onto the stack. And when we are doing this check, we will pop all the elements till we find a higher price. Let's say the top was 20. Then we next price is 30. So whenever next price comes, it will compare against 30 and not 20. Since it's a smaller, it's of no use. It will be skipped anyway. So we will see that if the current price, if the top price is less than today's price, then pop all the prices and spans which are less than the top's price. After that, you push the today's price and span. So that is optimization.